In this lecture, we're going to introduce the idea of inverse functions. We're going to define what it means for two functions to be inverses of one another and talk about how inverse functions interact under the operation of composition of functions. Our ultimate goal with inverse functions is to define logarithms. We're going to use inverse functions to define what a logarithm is. But in this lecture, we're going to treat the idea of inverse functions generally so that if you need them in another class, you'll be familiar with them. For instance, those of you headed on to trigonometry will talk about inverse trig functions. And so I want to give a general overview of what we mean by inverse functions rather than focusing specifically on logarithms. Before we can get to the definition of inverse functions, we need an intermediate definition of a one-to-one function. A function f with domain D and range R is a one-to-one function if either of the following equivalent conditions is satisfied. Either when a and b are different in the domain, then f of a and f of b are different in the range. Or whenever f of a and f of b are equal in the range, then a must have been equal to b in the domain. Kind of a short way to say this is that in a one-to-one function, different inputs yield different outputs. In a one-to-one function, if you plug in two different numbers, you're guaranteed to get two different answers. On the other side, if you can find any pair of different inputs that yield the same output, then the function is not one-to-one. And that's often an effective way to show that a function is not one-to-one. Here's an example of that. This example says, prove that g of x equals x squared plus 6 is not a one-to-one function. Now there are lots of possible pairs of numbers that will show that this function is not one-to-one. I think the most obvious pair is positive 1 and negative 1. If we plug positive 1 into this function, we get 1 squared plus 6, which is 1 plus 6, that's 7. And if we plug negative 1 into the function, we get negative 1 squared plus 6, but that's also 1 plus 6, which is 7. Since there are two different inputs that yield the same output, this function is not one-to-one. You just need to find one pair of numbers that violate the rule in order to show that a function is not one-to-one. Proving that a function is one-to-one is much more subtle. Here we want to prove that the function f of x equals negative 2x plus 5 is a one-to-one function. We're being told that it is, but we have to prove that it's true. Well, in a one-to-one function, whenever f of a equals f of b, then a must have been equal to b. So what I'm going to do is start by assuming that f of a is equal to f of b. F of a means plug a into the function. I get 2 times a plus 5. F of b means plug b into the function. I get negative 2 times b plus 5. If we can simplify this equation and show that the only way that this could happen is if that a was equal to b, then the function is one-to-one. So I would subtract 5 from both sides. That's negative 2a equals negative 2b. Then we divide both sides by negative 2. And we get a equals b. If f of a is equal to f of b, then it must be the case that a is equal to b. The only way that you can get the same output is if the two numbers you started with were equal. Therefore, this function is one-to-one. Now, oftentimes when people see this example, they wonder how this could ever unravel to anything besides a equals b. I mean, if you just replace x with a and b on each side, won't you always get a equals b? No, and let me show you that with the previous example. Here's that function g of x equals x squared plus 6. Let's assume that g of a equals g of b here. Well, that means that a squared plus 6 is equal to b squared plus 6. And it looks like we're just going to get a equals b, but watch what happens when we actually perform the algebra. We get a squared equals b squared, and now we use extraction of roots, right? And when we use extraction of roots, you must append a plus or minus to one side because this is an even root. So a might be equal to b, but a could also be equal to the opposite of b, and that's what we saw in our counterexample. We saw that g of 1 equals g of negative 1. That pair of inputs gave us the same output. Because there's a second case where the outputs are the same, this is not a one-to-one function. It is possible to find a pair of inputs that are different but yield the same output. So it won't always simplify down to a equals b. It will only do that if the functions are one-to-one. Now there's another visual approach to showing that a function is one-to-one, and that's to apply what's called the horizontal line test. We say that a function f is one-to-one if and only if every horizontal line intersects the graph of f in at most one point. If this reminds you of another rule, it's because we also know the vertical line test to see if a graph represents a function at all. If a graph passes the vertical line test, then that graph represents a function. If the graph of a function also passes the horizontal line test, then the function is one-to-one. The idea here is that on a horizontal line, all of the y-coordinates are the same. So if there's a horizontal line that touches the graph twice, that's two different x-coordinates that yield the same y-coordinate, two different inputs that yield the same output. That would not be one-to-one. If every horizontal line intersects the graph in at most one point, then you've got a one-to-one function. Here are the graphs of the two functions we just looked at. F of x equals negative 2x plus 5 would pass the horizontal line test. Every horizontal line touches the graph exactly once. This function is one-to-one. Our function g of x equals x squared plus 6 does not pass the horizontal line test. For example, I can draw this horizontal line right here that intersects the graph twice. That's two different x-coordinates that yield the same y-coordinate. That can't happen in a one-to-one function, and so this is not one-to-one. If you're dealing with functions whose graphs you're already familiar with, the horizontal line test is nice. So here are some examples of that. We're asked to determine if the following functions are one-to-one. In part A, we have f of x equals the square root of 9 minus x squared. Well, we know what that looks like. That's the upper half of a semicircle of radius 3 centered about the origin. That would not pass the horizontal line test, so this function is not one-to-one. If you want a specific example, if you plug in negative 3, you'll get 0, and if you plug in 3, you'll also get 0. Two different inputs that yield the same output. That can happen in a one-to-one function. B says g of x equals the absolute value of x minus 4. We know what that one looks like too. The absolute value functions are v-shaped. This one's going to have a vertex that sits 4 units to the right of the origin, so like right here. Does that pass the horizontal line test? No, it fails. And so this is not one-to-one. If you need a specific set of inputs that will yield the same output, try 3 and 5. If you plug 3 in there and 5 in there, you'll get the same answer. Part C says h of x equals x cubed plus 2. It's another shift of a library function. X cubed is the one that snakes through the origin. This one's been shifted up 2 units, so it's going to snake through the point 0, 2. That would pass the horizontal line test. This function is increasing over its entire domain. And if the function is always increasing, well then none of the y-coordinates can be the same, because the y-coordinates are getting bigger and bigger and bigger as you move to the right. So this is one-to-one. That logic can also be applied to a decreasing function. If you have a function that's decreasing over its entire domain, well then it has to be one-to-one because the y-coordinates are getting smaller and smaller and smaller, and therefore none of them can be the same. So we can show that functions are one-to-one using algebra, or we can show that functions are one-to-one using their graphs. Now why are we talking about one-to-one functions? In order for a function to have an inverse, it must be one-to-one. We'll explain why, but you'll see it's in the definition of an inverse function. It starts that way. Let f be a one-to-one function with domain D and range R. A function g with domain R and range D, that's not a misprint, we have flip-flopped those on purpose, is the inverse function of f, provided that the following condition is true for every x in D and every y in R. So here's how they're related. Y equals f of x if and only if x equals g of y. Now what does that mean? That says if you take a number and plug it into the function f, you'll get some output y. If you then take that value y and plug it into g, the output of that function will be x. So these functions kind of undo each other. They're inverses because they unravel one another. If you plug a number into f and take that output and plug it into g, you'll wind up right back to where you started. The reason we need f to be one-to-one is that we can't have two possible images to go back. If there are two x values that yield the same y, then when we go to g and try to reverse the process, there would be two possible outputs, but a function can't have two outputs for a single input. So in order for the inverse to be a function, we need this one-to-one property. Now this definition, like a lot of definitions, is hard to understand when you're just looking at this wall of text. All of the verbiage and all of the symbolism makes this harder to understand. But the concept is pretty easy, so we're going to investigate an example numerically. I claim that the function g of x equals the cube root of the binomial x minus 2 is the inverse function of the function f of x equals x cubed plus 2. We already know that x cubed plus 2 is a 1-to-1 function. It passed the horizontal line test. I'm claiming that the inverse of that is g of x equals the cube root of x minus 2. Let me show you how these interact. I'm going to plug a number into f, and then I'm going to take that output and plug it into g. You'll see we get right back to where we started every time. So for example, if I plug 0 into f, I get 0 cubed plus 2, and that of course is equal to 2. I'm now going to take that result, 2, and plug it into g. And when I do that, I get the cube root of 0, which is 0, and I wind up right back where I started. That's what this rule at the bottom is indicating will happen for inverse functions. They unravel each other. You get right back to where you started. It doesn't matter what number you pick. Let me do f of negative 5 just to be a little bit daring here. So that's negative 5 cubed plus 2. That's negative 123. Now I plug negative 123 into g, and I get the cube root of negative 123 minus 2, but that's the cube root of negative 125, which really is negative 5, and I'm right back to where I started. These two things match. It has to work in the other order too. Let me start with the function g. If I do g of 29, well, that's the cube root of 29 minus 2, which is the cube root of 27. That's 3. Let me evaluate f of 3. That's 3 cubed plus 2, that's 27 plus 2, and that's 29, and we're right back to where we started. I can in fact do this in general for any value a. All right, why mess around? F of a would be a cubed plus 2. If I plug a cubed plus 2 into g, I get the cube root of a cubed plus 2 minus 2. Well, those 2's cancel, and I get the cube root of a cubed, which is just a. It doesn't matter what number I start with, it always unravels back to the original, and that's why these are inverses. This last example might hint to you how we can show that two functions are inverses of one another. We're not writing it explicitly, but I hope you figured out what we're doing. This is composition of functions. In this last example, it's very glaring. I basically took the function f. Yeah, I plugged a into it instead of x, but that's basically the function f, and we plugged it into the function g, and it unraveled back to a. All of these examples were composition of functions. Here we did g of f of 0. We plugged 0 into f, and then we plugged that result into g. That's just g of f of 0. This was g of f of negative 5. This was f of g of 29. But generally all we're doing is composing functions, and that's where we get this theorem on inverse functions. Let f be a one-to-one function with domain D and range R. If g is a function with domain R and range D, then g is the inverse function of f if and only if both of the following conditions are true. G of f of x equals x for every x in D. X is in D because it's being plugged into the function f. F of g of y is equal to y for every y in R. Y has to be in R because R is the domain of g. Cutting to the chase again, let me cut through all of this. This basically says if you compose the functions in either order and get back to your original input, then the functions must be inverses. Let's prove that these two functions are inverses of one another. I claimed it on the previous slide. How can we prove that? Well, let's evaluate f of g of x. F is this function which cubes its input and then adds 2. And our input is the cube root of x minus 2. Well, when you cube the cube root of x minus 2, you just get x minus 2. Those 2's cancel, and you get x. These functions unravel each other. Whatever input you started with, that's going to be your output. G of f of x must also be x. You have to compose them in both orders. There are weird scenarios where you compose in one order and get x, but you compose in the other order and you don't. So you have to check both directions. We've basically already done this. We did it with a instead of x, but g of f of x would be plugging f of x into the function g. Well, g is this function which subtracts 2 from its input and then takes the cube root. Our input is the function f, which is x cubed plus 2. The 2's cancel. Again, we've already seen this. We take the cube root of x cubed and we get x. Because we got x in both directions, these functions are inverse. You can almost see it if you talk your way through it. Look what f does. F starts by cubing its input and then adding 2. Everything g does is to unravel what f does. f starts by cubing an expression, g ends by finding the cube root of an expression. F adds 2 at the end, g starts off by subtracting 2. So whatever f does, g immediately undoes it. So here's another example. Prove that f of x equals 6x minus 11 and g of x equals 1/6 x plus 11/6 are inverse functions of each other. F of g of x, well, f is this function that multiplies its input by 6 and then subtracts 11. The function g is 1/6 x plus 11/6, and it's already becoming clear why g of x has to be expressed this way. This 6 is going to come multiplying through here and cancel out those fractions. This becomes x plus 11 minus 11, and yeah, that's just x. G of f of x, well, g takes its input times 1/6 and then adds 11/6. The input is the function f, which is 6x minus 11, and now we see why we have to add this fraction onto the end. When the 1/6 comes through, 1/6 of 6x is x, but 1/6 of negative 11 is negative 11/6. So the plus 11/6 cancels that away, and we again just get x. So these examples show how inverse functions interact. They kind of undo each other. And this is how we're going to apply inverse functions in our class. We're going to have these equations where the variable is trapped up in the exponent, and we're going to need to unravel that expression in some way. And we're going to use the inverse function of that exponential function in order to do that. I'm kind of foreshadowing a little bit, so if you're not exactly sure what I'm talking about, that's okay. But that's really where we're going with this, is to use this unraveling idea to help us solve equations or something like that. One more example to show how these functions interact. I want you to try to do this one. Suppose f of x and g of x are inverse functions such that f of 5 equals negative 2 and g of 7 equals 3. I want you to find f of 3 and g of negative 2. And at first this looks hard because we don't know what the functions f and g are, so how could we possibly find these outputs? But I want you to think about how we can use the fact that f and g are inverses in order to answer this. Okay, how would this work? If f and g are inverses, then f of 3 has to be equal to the input to g that would yield an answer of 3. And hey, we were given that. We know that g of 7 is 3. F of 3 must be 7, and the logic is that that's because g of 7 is equal to 3. They're inverses of one another. If you weren't sure how to do the second one, try that one now. Right, it's the same logic. G of negative 2 must be equal to 5, and we know that because we were told that f of 5 was equal to negative 2. That's how inverse functions are related to one another. Their inputs and outputs flip-flop. It's like you're flip-flopping their domains and ranges. Or another way to explain it is in the graph, you're flip-flopping the x and y coordinates of every point. So that ends our introduction to inverse functions. In a future lecture, we're going to talk about how you can find the inverse function of a given function in certain situations. So rather than just showing that two functions are inverses of one another, we're going to discover the inverse function for a given function. We'll also talk more about how these functions interact with one another. If you have any questions about what it means for a function to be one-to-one, or why we had to define one-to-one at all, what it means for two functions to be inverses of one another, or how inverse functions interact, please reach out to me. You can see me in an office hour or just send me some emails.